today we're going to be talking about what a polynomial is and everything that goes along with it. So, we have to first define what a polynomial is. A polynomial is a sum of terms where all the variables have whole number exponents and no variables in the denominator. With some examples, we know that the linear function is x to the first. It looks like this, my graph. For the quadratic function, it's x raised to the second, x squared. And that's what it looks like. Cubic function is x to the third. Looks like this. Sort of, kind of S shape. And our quartic function is x to the fourth. But it varies slightly, and it flattens out, and then it goes back up. So, now that we have all of our graphic representations, that's how we know we can look at a graph and say, okay, this is a different function than the other one. But now what we need to talk about is the degree and how we can determine that based off of the rate of change and looking at a table. So, the degree. What is a degree? The degree is the highest exponent in the function, but it also determines the end behavior, which we'll get to later. The end behavior we'll get to later. For a linear function, the rate of change is constant. So that's where it'll tie in with the degree, because we'll have -3, -2, -1, 0, 1, 2, and 3. And the rate of change for all of these is just 1. Right? So the rate of change for all of these is just 1. And that's how we know that it's a constant rate of change. Plus, we only have to find the rate of change once, which also ties in with the degree. For a quadratic function, it's a little different. We have +9, +4, +1, 0, 1, 4, and 9. They're going to be positive because they're both facing up, which is going to tie into the end behavior later as well. For our rate of change, we're looking at a quadratic function. And initially our rate of change is going to be subtracting 5, subtracting 3, subtracting 1, adding 1, adding 3, and adding 5. Now that's not constant like the linear function was, so we need to try again, see if we can maybe get a constant this time. So now this is adding 2, adding 2, adding 2 because -1 + 2 equals +1, adding 2, and adding 2. So this is our constant rate of change. But then, what does that make this rate of change? It makes it linear, because we see this kind of lines up with this, right? So this is linear. Our initial rate of change is linear. And that's how we know that we have a degree of 2, also known as having a quadratic. For our cubic function, it's going to look even weirder because now we have negatives and positives, just like the linear function, except it's at a different rate of change. Here we're going to have -27, -8, -1, 0, 0, 1, 8, and 27. Our initial rate of change, we already know because of the quadratic that it's not going to be constant. So, we're going to have +19, +7, +1, +1, +7, and +19, right? So at that, we know that's not constant. So now we have to keep going until we get a constant rate of change. This is going to be -12, -6, -0, because in this one, obviously, there's no change there. 6 and plus 12. So we still don't have a constant rate of change. We're going to do it one more time. And we have plus 6, plus 6, plus 6, and plus 6. So we have a third difference here. We have this one, and this one. We know that these are, this is linear. This is constant, because that's why it has the same number here. But then this one must have to be quadratic. Because we see that the quadratic has a second difference. And just like the linear moved down here, and that was the initial rate of change, that must mean that the quadratic is going to be our initial rate of change for our cubic function. Our values here in the table, and we're going to have our rate of change just like we did before, and we're just going to keep going with our rate of change until we get a constant value, because that's how we know we've got the right rate of change for the degree. So we're going to have negative 65, negative 15, negative 1, positive 1, positive 15, and positive 65. Keep going with our rate of change. Here we have positive 50, positive 14, positive 2, positive 14, and positive 50 again. Notice how this pattern is following the shape of the parabola, where it's just following the pattern here. Then we have positive 24. No, we're not going to have positive 24. We're going to have wait a second. 1, 2,
Negative 36.
negative 36, that's right. Thank you, Assistant Matthew. Negative 36. Negative 12. Positive 12. No.
Yes.
Yes, okay, negative 36. Negative 12. Negative 12. Positive 12. And positive 36. We can do math, guys. Struggling here. And now we're going to have positive 24, positive 24, and positive 24. So here's our constant rate of change that we were looking for this whole time and went through that entire process for. We've got our linear rate of change. That guy's there. We've got our quadratic rate of change. And that just leaves our cubic rate of change. So, that is how the rate of change ties in with the degree of a function. However many times you have to do the difference is how the number of the degree will be. Plus, you also know that you had, so you have to do it 4 times for this one. 1, 2, 3, 4. Degree of 4. 1, 2, 3. Degree of 3. 1, 2, degree of 2, and just once to get your constant. And that's how that works. So, since we already have this, now we have to remember what we observed earlier, which was the end behavior and how it affects the numbers that we're working with here, whether they're negative and positive or if they're just all positive. With an even number in the degree, even, our end behavior is going to be different than the one with the odd one. So end behavior for an even degree is that as x approaches negative infinity, y is also going to approach infinity instead of negative infinity. And as x approaches infinity, y is going to approach infinity once again. So that gives us this shape of just the parabola. And for our degrees that are odd degrees, our end behavior is going to be as x approaches negative infinity, y is also going to approach negative infinity. And as x approaches infinity, y is going to follow that pattern and follow infinity, go to approach infinity. So these are two separate end behaviors because that's the shape of that one. On a graph. No, on a graph. Right? And so end behavior is affected by the degree. Rate of change is affected by the degree. And they all tie together. That's pretty much how you can identify almost everything in the standard form of a polynomial function. You have your degree, your rate of change, and your end behavior just by looking at the degree. So if we have an odd degree, we can already tell you what the end behavior is going to be. And depending on what the degree is, we can tell you what the rate of change is. So if I were to have a quintic function, a quintic polynomial function, I would know that the rate of change initially would be quartic. Because I would know that I would have to find the fifth difference to find my constant value for the quintic polynomial function. So that is the end of our video.